All right, so our next section is going to be 3.5. This is mostly going to be a review of transformations of functions or graph shifting, and a couple of parent functions, but we're also going to look at one or two other topics in here as well. So I am going to move through the graph shifting stuff kind of quickly because you've seen this in Alg 2, you've seen this in pre-calc. This should be stuff that you are fairly common or fairly familiar with because it should be common knowledge to you at this point. So we have a couple of parent functions here. I would go through the slides on your own and make sure you are comfortable not only with obviously the names of each parent function, but then the parent equation. Let me come to a different one. A parent equation, the general equation, whether you have a vertex or a or whatever you have for a locator point, whether it's an endpoint, inflection, so on and so forth. Your domain and range, and then also the critical points for that particular graph, and as well the general shape of the graph, right? So the ones that you should be familiar with, technically linear functions are a parent function as well, but really the first one you learn is absolute value. You should be familiar with your quadratic functions. You should be comfortable with cubics, square roots, cube roots, and reciprocal functions as well. I also have the reciprocal squared function in here, although this one's probably newer. It is covered in our book, so you may see this pop up in some of your homework as well. There's a whole section of all of these functions with the way the book shows them to you within 3.5. So please feel free to take a look at that in there as well. All right, so in terms of our family functions and our graph shifting, each graph is really could be broken down into some parent function with a series of shifts, stretches, compressions, different manipulations to that original parent function to get the end result. Okay, so again, we could have something that's stretching it, making it tall and skinny, and a vertical stretch. We also, in terms of trig, you would have seen period changes, which were horizontal stretches or compressions, which are stretching or compressing something in a horizontal direction as well. You're going to see some shifts in the left, right, up, and down directions. We're also going to see reflections where something maybe flips over the x, or also possibly horizontally over the y-axis as well. Okay. Again, vertical stretch is multiplying, which I have, and let me use the absolute value one. So y equals a times the absolute value, and I'm going to put a bx minus h inside absolute value and plus k. So if I have a vertical stretch, I'm going to have some a value out here that's going to multiply and change all of my y values by whatever factor a we have. If it's a stretch, a is greater than 1. If I have a vertical shrink or a vertical compression, I have an a value that is between 0 and 1. And again, it's multiplying all the y values by that same number, so maybe 1/2 or 1/3. Horizontal compression would be this component right here, the b inside of the function. So if I have a number times my variable x inside of the function, that's going to cause a horizontal stretch or compression. So it's going to compress it horizontally, which in non-periodic functions is going to look like a vertical stretch. So if I take something and make it really, really skinny, it only has one place to go, and that's going to be essentially up. It's going to have to look taller, even though it's a horizontal compression. Where it's going to divide all of my x values by whatever that horizontal compression factor b is, assuming it's greater than 1. A horizontal stretch is going to divide all the x values by the same factor. If it is between 0 and 1, it's going to stretch it out. Think about your periodic functions. If I had, sine of 4x, it's going to cycle through the sine function 4 times as fast as sine of x. Therefore, we're going to have a horizontal compression. It divided all those x values by 4, right? So hopefully that makes sense, and hopefully you guys are following that. Worst case scenario, we could talk about that when we are in class tomorrow, and we can do a little bit more with that. All right, so all the different shifts, compressions, everything else is here. And let me get to the general equation, and actually let me just come back to the one I had here. anything that's happening inside of the function, this is going to cause our left-right shifts. Essentially anywhere, if I were to solve whatever that quantity is and get x equals, in this case it would be h over b, this would give me my left or right shift of the particular function, right? Wherever that quantity equals 0, that's where the center of our function is going to occur. This quantity on the outside, this is going to cause my vertical shift up or down. And really our, horizontal or vertical stretches don't really affect the amount of vertical shift. However, the amount of horizontal compression does actually affect the amount of horizontal shift should there be both occurring at the same time. Okay. And then obviously A is going to cause our vertical stretch compression, which we already talked about here. So let's take a look at one or two examples. So here I just have a basic example. I'm going to go through. This is a absolute value function. I'm going to graph the function up here. Y equals -3 times the absolute value of x minus 2 plus 4. So in terms of graph shifting, three-step process, we want to sketch the parent function. This is absolute value. So in blue, I'm going to sketch y equals absolute value of x. So I have critical points at 0, 0, 1, 1, and 2, 2. And I'm going to have points at -1, -2, 2. The function looks something like this. In orange, then, what I'm going to do is I'm going to multiply by my stretch factors, right? And if we have a horizontal compression as well, we're going to deal with that here in step 2 also. Okay, so any of our horizontal or vertical stretches or compressions are going to take place in step 2. In this case, it's just a vertical stretch, and actually here it's also going to flip. So I'm going to multiply my y values of the parent function by, in this case, the a value, which is -3. So 0 is going to remain 0. My y values of 1 are going to become -3s. And my y values that were 2s are going to now become -6s. And what I'm going to get is a graph that has now flipped upside down and stretched out by a factor of 3. Okay, and in my very last step then, and we're going to switch over to red, now I'm going to shift it according to my locator. So inside is opposite, right? Because I would have to solve that. So if I solve x minus 2 equal to 0, I'm going to end up with x equals +2. Thus, inside is opposite. We're going to go 2 to the right, and then we're going to go up 4. So if I take each of these points that I have here graphed in orange, okay, and if I take each of those points and I move them 2 to the right and up 4, I should have points that end up right here. Okay, I want to do that in red though, so I just wanted to do that so you guys can see the actual shift itself. All right, so we're going to take, and in red, 2 to the right and up 4, my vertex is going to be at 2, 4. We're going to have points here, 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 and here, giving me a graph. It's going to look something about like this. Okay, so when we're doing graph shifting, I always teach this as a 3-step process. You're going to graph the parent function, then you're going to graph the parent function with all of its horizontal and or vertical stretches or compressions. We do that second because everything is relative to a starting point essentially of 0, 0, and a center point, if you will, of the graph of 0, 0. Right? And it's important, if we're going to do it by just multiplying the y or possibly x values by either a or b, that we do this before we shift it, because once we shift it, I can no longer simply multiply by some quantity. Okay, now I have to remember ratios, and those ratios are different for every single function, and it just adds complexity that we really don't need. All right, let's take a look at one more example here. And in my second example, we're going to graph y equals 2 times the quantity x plus 3 squared minus 4. Remember, inside is opposite, so the x plus 3 equals 0. We're going to get x equals negative 3. So this shift is going to be left 3 and down 4. I have an a value of 2, which means it's going to stretch it vertically by a factor of 2. So if I start with my parent function, quadratics, we're going to 0, 0, 1, 1, and 2, 4, negative 1, 1, and negative 2, 4. And we're going to have a parent function that looks something like this. And make those points a little bit more pronounced. My line was a little thicker. All right. Now I want to take, and in orange, I'm going to stretch this function by a factor of 2. I'm going to multiply each of these y coordinates by 2. So 0 is still going to be 2. My 1s are going to become 2s, and my 4s are going to become 8s. All right, so what we're going to end up with here something that's going to look like that. Okay, my graph got twice as tall, it got taller and skinny. All right, and now I'm going to shift it in red according to my vertex, so it's going to go 3 to the left and down 4. So I'm going to have a vertex here at 3, negative 3, negative 4, and we're going to have the following points. I'm going to end up with a final graph. Should look something like this. All right. So again, 3-step process. Graph your parent function, then multiply your y coordinates by a, your x coordinates you're going to divide by b if b exists, and then you're going to shift that stretched or compressed graph left, right, up, and down according to h and k, or again, if you have both a horizontal shift and a horizontal compression, you need to go with that h over b value for your left, right shifts. All right. I have a series of problems here for you. I want you guys to try a couple of these. I may throw a couple of them out there, and we're going to try a couple in class tomorrow. But it probably wouldn't be a bad idea to go through, practice a few of these, just make sure you're good to go, knock the rust off, and make sure we're all speaking the same language in terms of graph shifting and reflections. The last thing I want to mention in here is even and odd functions. All right, we talked about symmetries the other week in terms of equations. So we could have symmetry about the x-axis, symmetry about the y-axis, or symmetry about the origin. When we talk about functions, obviously symmetry about the x-axis kind of goes out the window, because if I have symmetry about the x-axis, that also means I'm failing my vertical line test. So when we talk about even and odd functions, really we have 2 different types of symmetry. There's symmetry about the y-axis and symmetry about the origin. Right? So an even function is one that has symmetry with respect to the y-axis. Our test for an even function is we're going to evaluate an f of negative x, and we're going to see, and we're going to ask ourselves, do we get the original f of x in return? Probably looks really familiar, because before we replaced x with negative x, and we looked to see if we got the same equation back for y-axis symmetry. Right? When we go to evaluate for an odd function, we're going to evaluate f of negative x. And I want to see and find out, do I get the opposite of my original function, f of x? So do all of my terms within that function, do they change sign so I can factor in -1 out? Okay. We're going to do a couple more of these. We're going to do a few of these in class. But it's really the exact same thing as what we have done prior with symmetry with equations. Now we're just doing it in terms of function notation. So I'm not going to be redundant and beat the dead horse and go over and do multiple examples of this here in the notes, because I think we've already covered that adequately. But we can do more in class tomorrow if need be. All right. So that's all I've got in terms of our section 3.5 notes. Hope you guys have a good night, and we'll see you tomorrow.